Welcome to Sleeping Researcher, your gentle companion for drifting into restful sleep through the soothing narration of fascinating scientific topics. Our channel invites you to explore the wonders of the universe at a relaxed pace, where curiosity meets calmness and knowledge becomes a lullaby. Before we begin our journey tonight, I gently encourage you to like this video and subscribe to Sleeping Researcher. By joining our peaceful community, you support the creation of more serene science stories designed to calm your mind and help you unwind. Tonight, we embark on a quiet exploration of terraforming planets, the remarkable idea of transforming distant worlds into habitable places. Imagine the possibility of turning barren landscapes into thriving environments where life as we know it could one day flourish beyond Earth. We will softly uncover what terraforming means, the scientific challenges it presents, and the hopeful dreams it inspires for humanity's future among the stars. So, settle into a comfortable position, breathe slowly, and let your mind gently wander as we begin this tranquil voyage into the art and science of shaping new worlds. Imagine a distant world, barren and silent, slowly awakening under the gentle touch of human ingenuity. Terraforming, the ambitious pursuit of transforming planets to support human life, invites us to envision a future where the boundaries of Earth no longer limit our existence. This profound concept captures the imagination, blending the rigor of science with the boundless possibilities of exploration. At its core, terraforming seeks to alter the atmosphere, temperature, surface topography, or ecology of another planet, crafting an environment hospitable enough for humans to inhabit and thrive. It is a vision that has inspired scientists, authors, and dreamers alike, promising not only new homes among the stars, but also a deeper understanding of the delicate balance that sustains life itself. The challenges inherent in terraforming are as vast as the cosmos itself. To initiate life-supporting conditions on a planet, one must consider complex factors such as atmospheric composition, availability of water, and adequate protection from harmful radiation. Mars, often regarded as the prime candidate for terraforming, presents a particularly intriguing case. Its thin atmosphere, composed mostly of carbon dioxide, and surface temperatures that can plunge dramatically, pose significant obstacles. Yet, through gradual and deliberate modification, such as releasing greenhouse gases to warm the planet or introducing photosynthetic organisms to generate oxygen, the dream of making Mars more Earth-like remains within the realm of possibility. These scientific endeavors require patience, precision, and an unwavering commitment to understanding planetary ecosystems. In this way, terraforming challenges us to extend our stewardship beyond Earth, contemplating the ethical and practical dimensions of reshaping entire worlds. Beyond the technical aspects, terraforming also invites profound philosophical reflection. What does it mean to alter a planet's natural state? How might such transformations affect potential indigenous life forms, even if microscopic or dormant? The process compels humanity to consider its role not merely as explorers, but as caretakers and creators. It asks us to balance ambition with responsibility, ensuring that our expansion into space respects the intrinsic value of other worlds. These questions are vital as we look toward a future where space travel and colonization grow ever more feasible. The pursuit of terraforming embodies a harmonious blend of hope and caution, sparking curiosity about what lies ahead for our species. Each step taken in this direction not only advances our technological prowess, but also deepens our connection to the universe we inhabit. As humanity continues to grow in numbers and technological capability, the limitations of our home planet become increasingly apparent. Earth's resources, while abundant, are not infinite. The strains of overpopulation, environmental degradation, and the relentless consumption of natural materials have begun to challenge the delicate balance that sustains life here. In this context, the idea of terraforming other planets emerges not just as a scientific ambition, but as a potential necessity. By transforming distant worlds into habitable environments, we open new frontiers that could alleviate the pressures on Earth's ecosystems. This vision extends beyond mere expansion. It represents a profound opportunity to ensure the survival and flourishing of human civilization. The motivation to terraform is deeply intertwined with our instinct to endure, adapt, and thrive in the face of planetary limitations. Moreover, terraforming offers a unique avenue to access vast new reservoirs of resources. Planets and moons within our solar system and beyond harbor minerals, water, and energy sources that could support not only local colonies, but also the needs of Earth itself. As terrestrial reserves dwindle, the ability to cultivate self-sustaining habitats on other worlds presents a strategic solution. This approach could help reduce the environmental impact of resource extraction on Earth, preserving its natural landscapes and biodiversity. The prospect of creating ecosystems suited to human life also invites us to rethink how we manage and steward planetary environments, applying the lessons learned here to foster harmony and sustainability elsewhere. In this way, terraforming becomes not only an act of survival, but an extension of our responsibility to live in balance with nature. The drive to terraform also reflects a deeper, almost philosophical longing to explore and inhabit new worlds. Humanity's history is marked by journeys into the unknown, driven by curiosity, hope, and the desire for a better future. Terraforming embodies this spirit on a cosmic scale, offering a chance to reshape barren landscapes into thriving habitats. It challenges us to harness our scientific knowledge and creativity to overcome immense challenges, altering atmospheres, regulating climates, and establishing life-supporting conditions. While the technical hurdles are formidable, the potential rewards extend beyond survival. They include the opportunity to redefine our place in the universe, to cultivate new civilizations, and to ensure that life, in its varied forms, continues to expand across the cosmos. This pursuit calls for patience, wisdom, and a respectful humility toward the worlds we touch. It is also important to recognize the ethical dimensions embedded in the motivation to terraform. The act of transforming another planet carries with it the responsibility to consider the potential existence of indigenous life, however simple or dormant it might be. This awareness demands a careful and respectful approach, balancing human aspirations with the preservation of extraterrestrial environments. As we contemplate terraforming, we engage in a dialogue between science and ethics, technology and stewardship. The decisions made today will echo far into the future, shaping the legacy we leave among the stars. This interplay of ambition and caution forms the foundation upon which our cosmic endeavors must be built. In embracing this challenge, humanity steps into a role that is as much about care as it is about conquest. At the heart of terraforming lies a profound understanding of planetary science and environmental engineering. To transform a distant world into a habitat capable of supporting human life, we must first comprehend the delicate balance of atmospheric composition, temperature regulation, and surface conditions. Each planet presents its own unique set of challenges, from the thin carbon dioxide-rich atmosphere of Mars to the crushing pressure and toxic gases enveloping Venus. The science of terraforming requires us to manipulate these variables gradually and carefully, often over centuries, to create a stable and sustainable environment. This process begins by envisioning the planet not simply as a celestial body, but as a complex system where geology, chemistry, and biology interact in subtle and dynamic ways. The task involves replicating elements of Earth's life-supporting environment. Oxygen levels suitable for respiration, temperatures within a range hospitable to liquid water, and protection from harmful radiation. These scientific principles are the foundation upon which terraforming rests, guiding our efforts as we seek to rewrite the conditions of worlds far beyond our own. Central to this endeavor is the manipulation of planetary atmospheres, a challenge that requires both innovation and patience. For Mars, one proposed method involves releasing greenhouse gases to trap heat and gradually warm the surface, encouraging the sublimation of polar ice caps and the release of carbon dioxide to thicken the atmosphere. This thickened atmosphere would help retain heat and potentially support liquid water on the surface. Conversely, on Venus, the problem is one of excess heat and dense, toxic gases. Here, ideas range from deploying reflective shades in space to chemically altering the atmosphere to reduce its greenhouse effect. Each approach demands a careful balance of physical laws and chemical reactions, relying on a deep understanding of atmospheric dynamics and planetary geology. These scientific insights inform not only what is possible, but also the timescales required for such monumental changes. The complexity of these processes underscores the intricate dance between natural planetary systems and human technological intervention. Beyond atmospheric considerations, Terraforming also involves the introduction and support of life forms capable of sustaining an ecosystem. The concept of biospheres, self-regulating environments where biological and chemical cycles maintain balance, is crucial to this step. Scientists imagine seeding planets with hardy microorganisms, such as extremophiles, which can survive in harsh conditions and begin the slow transformation of the soil and atmosphere. These organisms could help produce oxygen, break down minerals, and create the building blocks necessary for more complex life. This biological engineering must proceed with caution, as introducing life to a new world carries risks and uncertainties, both ecological and ethical. The interplay between biological processes and physical environments must be carefully modeled and monitored to ensure that each step toward habitability remains controlled and reversible if necessary. This scientific synergy between microbiology, ecology, and planetary science forms the living heart of terraforming research. The feasibility of terraforming also depends on advances in technology and resource management. From robotic explorers and automated factories to sophisticated climate control systems, humanity's capacity to alter planetary environments hinges on our ability to deploy and sustain large-scale engineering projects across vast distances. Concepts such as orbital mirrors to reflect sunlight, magnetic shields to protect atmospheres from solar wind, and the mining of local materials for construction and fuel illustrate the breadth of scientific ingenuity required. Energy considerations, logistics, and the longevity of equipment in hostile environments all factor into the planning and execution of terraforming missions. These technical challenges demand a multidisciplinary approach, integrating astrophysics, robotics, environmental science, and more. Each technological stride brings us closer to turning distant dreams into tangible realities, yet also reminds us of the immense scale and complexity inherent in reshaping other worlds. Understanding the science behind terraforming invites us to appreciate both the promise and the profound responsibility embedded in this endeavor. It is a testament to human curiosity and resilience that we contemplate reshaping entire planets. Yet this vision also requires humility and respect for the unknown. Scientific exploration continues to reveal new insights about planetary environments, pushing the boundaries of what we might achieve while cautioning us about the delicate balances we must maintain. As we deepen our knowledge and refine our methods, the dialogue between science and ethics grows ever more vital, ensuring that our steps forward remain thoughtful and deliberate. In embracing the scientific principles of terraforming, we prepare not only to expand our horizons, but also to safeguard the integrity of the cosmos we seek to inhabit. The first step in the intricate process of terraforming is the careful selection of a planetary candidate whose natural conditions offer a foundation upon which life-supporting environments can be established. Not every celestial body is equally suited for such transformation. Scientists must weigh numerous factors, among which the presence and composition of the atmosphere stand paramount. A planet with a dense, stable atmosphere can regulate temperature and protect emerging ecosystems from harmful cosmic radiation. Conversely, worlds with thin or non-existent atmospheres present formidable challenges, requiring extensive intervention to create breathable air and shielded environments. Understanding these atmospheric qualities not only informs us about the feasibility of terraforming, but also guides the technological pathways we must develop. For example, planets rich in carbon dioxide might allow for the introduction of photosynthetic organisms to gradually alter atmospheric gases, thereby creating a more hospitable climate. Such strategic choices underscore the importance of meticulous observation and analysis before any physical alteration begins. Temperature is another critical aspect in determining a planet's suitability for terraforming. The thermal environment influences everything from chemical reactions in the soil to the ability of water to exist in liquid form, a cornerstone for life as we understand it. Ideally, the target planet would reside within its star's habitable zone, where temperatures allow for stable bodies of liquid water. However, many planets fall outside this ideal range, either too cold or excessively hot, presenting unique challenges. If a planet is too cold, methods such as greenhouse gas introduction might be employed to raise surface temperatures gradually. Alternatively, if a planet is too hot, reflective aerosols or orbital adjustments could help mitigate excessive heat. These interventions require profound understanding of planetary climates and the delicate interplay of atmospheric components, reminding us that terraforming is a process of subtle balance rather than brute force. Choosing a planet with temperature conditions that are not too extreme can significantly ease the path toward creating a sustainable environment. The presence and availability of water in any form is perhaps the most compelling criterion in choosing a planet for terraforming. Water is essential for all known life, acting as a solvent for biochemical reactions and a medium for nutrient transport. Planets with existing water reservoirs, whether as ice, vapor, or liquid, offer a profound advantage. The availability of water correlates directly with potential habitability and the ability to support complex life forms. In some cases, subterranean ice or polar caps might serve as sources to be gradually harnessed and redistributed. However, planets entirely devoid of water present a daunting challenge, requiring the importation or synthesis of this vital resource, an endeavor both technologically and energetically demanding. Thus, selecting a planet with accessible water not only facilitates the initial stages of terraforming, but also ensures the long-term stability of ecosystems that might one day flourish there. This consideration anchors our efforts in the principles of sustainability and respect for planetary resources. Beyond atmosphere, temperature, and water, other factors contribute to the complex decision-making process involved in selecting a planet for terraforming. The planet's size and gravity influence its ability to retain an atmosphere and support liquid water on its surface. Magnetic fields, if present, play a crucial role in shielding the planet from solar and cosmic radiation, preserving atmospheric integrity over time. Additionally, Geological activity can replenish atmospheric gases and recycle nutrients, supporting dynamic and resilient ecosystems. Each of these elements weaves into a delicate tapestry, painting a picture of a world either ripe for transformation or one requiring monumental effort to adapt. The interplay of these scientific criteria invites us to approach terraforming with both precision and patience, recognizing that the path to creating a new home among the stars is as much about understanding as it is about innovation. The process of identifying an ideal planet is thus a profound exercise in balancing ambition with pragmatism, guided by careful study of environmental conditions and planetary characteristics. It is a journey that demands collaboration across disciplines, from astrophysics and geology to biology and environmental science, each contributing vital insights as we refine our selection criteria and deepen our knowledge of distant worlds. We prepare to embark on the next phases of terraforming, where theory meets practice in the transformation of barren landscapes into thriving habitats. This thoughtful approach ensures that when the time comes to begin altering a planet's surface and atmosphere, our actions will be informed, deliberate, and respectful of the complex systems we seek to harmonize. Among the many celestial bodies that capture human imagination, Mars stands out as the prime candidate for terraforming. Its appeal lies not only in its proximity to Earth, but also in the striking similarities that suggest a foundation upon which life-supporting environments could be built. Mars possesses a day length closely matching Earth's, lasting just over 24 hours, which offers a familiar rhythm to potential settlers. Its surface gravity, while weaker than Earth's, is sufficient to retain an atmosphere and allow for human mobility without excessive strain. These characteristics, combined with the presence of polar ice caps and evidence of ancient water flows, paint a picture of a planet that may once have harbored conditions amenable to life. The ongoing exploration missions such as rovers and orbiters have been instrumental in deepening our understanding of Mars's geology and climate, providing crucial data that informs terraforming strategies. As we study the red planet, we uncover not only its challenges, such as thin atmospheric pressure and temperature extremes, but also its latent potential to be transformed through careful and sustained intervention. Current scientific efforts on Mars are laying the groundwork for future terraforming endeavors, highlighting the importance of incremental progress. Robotic missions have analyzed soil composition, searched for organic molecules, and monitored seasonal atmospheric changes, revealing a dynamic environment that, while harsh, is not entirely inhospitable. The presence of carbon dioxide in the Martian atmosphere offers a resource that could be harnessed in producing oxygen through chemical processes such as electrolysis. Moreover, the frozen water at the poles and beneath the surface provides an essential ingredient for sustaining life and potentially generating breathable air. By leveraging these existing elements, terraforming plans envision a gradual thickening of the atmosphere and warming of the planet, which would encourage the development of liquid water on the surface and the eventual establishment of ecosystems. These scientific foundations are vital as they allow us to approach terraforming with a realistic appreciation of the planet's current state and the transformative steps required. Mars's position within the solar system also contributes to its suitability. offering a balance between environmental conditions and accessibility. Being relatively close to Earth, it presents logistical advantages for sending supplies, equipment, and eventually human explorers. This proximity facilitates continuous study and adaptation of terraforming techniques, enabling a feedback loop that refines our approaches based on real-time data. The planet's thin atmosphere and lack of a global magnetic field pose challenges in protecting future inhabitants from cosmic radiation. However, these obstacles inspire innovative solutions, from artificial magnetic shields to subterranean habitats. The ongoing human fascination with Mars, reflected in decades of missions and scientific inquiry, has cultivated a growing pool of knowledge and technology aimed at overcoming these hurdles. As such, Mars embodies a compelling intersection of scientific possibility and human aspiration, making it the leading candidate for transforming a distant world into a new home. The momentum generated by current and planned Mars missions reinforces the planet's role at the forefront of terraforming discourse. International collaborations continue to design and test technologies aimed at life support, sustainable energy, and habitat construction, addressing the multifaceted challenges of living beyond Earth. Simultaneously, advancements in planetary science refine our understanding of Mars's climate cycles, geological activity, and potential biosignatures, all of which inform the ethical and practical dimensions of terraforming. This synergy between exploration and research ensures that future efforts to alter Mars's environment will be grounded in comprehensive knowledge and a commitment to stewardship. As we stand on the threshold of turning science fiction into reality, Mars beckons as a laboratory for planetary transformation, inviting humanity to deepen its relationship with the cosmos. Mars presents a unique atmospheric challenge that must be carefully considered in any terraforming effort. Unlike Earth, whose atmosphere is rich in nitrogen and oxygen, Mars's air is composed predominantly of carbon dioxide, making up about 95% of its thin envelope. This sparse atmosphere exerts only about 1% of the pressure found at Earth's surface, which is insufficient to support human respiration or liquid water stability. The low atmospheric density also means that Mars offers little protection from cosmic radiation and solar winds, factors that threaten both human health and the integrity of potential habitats. These conditions necessitate the development of technologies capable of generating a breathable atmosphere, while simultaneously addressing the hazards posed by radiation and temperature extremes. Understanding these atmospheric properties is essential for defining the scope of terraforming, as it sets the baseline for what must be altered or supplemented to create a safe, sustainable environment for future explorers and settlers. The dominance of carbon dioxide in the Martian atmosphere poses significant obstacles for creating a breathable environment, while CO2 is critical for sustaining plant life through photosynthesis. the sheer volume present on Mars is not directly usable by humans and must be transformed or removed to increase oxygen levels. Additionally, the thin atmosphere fails to retain heat, contributing to wide temperature fluctuations that can plunge to extremes far below those tolerable for human life. Efforts to thicken the atmosphere by releasing greenhouse gases or sublimating polar ice caps could help raise temperatures and pressure, but these processes are slow and require immense energy and resources. The balance between increasing atmospheric density and maintaining environmental stability demands precise control and detailed understanding of Martian climate dynamics. The challenge lies not only in producing oxygen, but also in stabilizing the atmosphere to support liquid water and protect against harmful radiation, creating a complex puzzle at the heart of planetary engineering. Beyond the chemical composition, the Martian atmosphere's interaction with the planet's surface and magnetic field adds further complexity. Unlike Earth, Mars lacks a strong global magnetic field, allowing solar winds to strip away atmospheric particles over time, which contributes to its current tenuous state. Any terraforming strategy must therefore consider ways to replenish and maintain the atmosphere in the face of this continuous loss. Some proposals suggest creating artificial magnetic shields or localized fields to protect the atmosphere and future colonies. Moreover, the regolith or surface soil contains perchlorates and other toxic chemicals that could be released into the atmosphere or ecosystems if disturbed, posing additional risks. Addressing these challenges involves interdisciplinary research spanning planetary science, chemistry, and engineering, underscoring the intricate nature of reshaping an alien environment. The thin CO2-heavy atmosphere of Mars is a reminder that terraforming is not merely a technical challenge, but also a delicate balancing act with the planet's natural systems. The quest to create a breathable atmosphere on Mars engages both imagination and rigorous science, inviting us to confront the realities of planetary engineering. Technologies such as atmospheric processors, capable of extracting oxygen from carbon dioxide, or large-scale greenhouses designed to cultivate microbes and plants, offer promising avenues for gradually transforming the air. Yet these solutions must be integrated within a broader understanding of Martian weather patterns, dust storms, and seasonal changes, which can influence atmospheric composition and stability. Continuous monitoring and adaptive management will be essential as any terraforming endeavor unfolds over decades or centuries. This patient approach reflects the profound respect required when altering a planet's environment, emphasizing that success depends on harmonizing human ambition with natural planetary processes. As we delve deeper into the complexities of Mars's atmosphere, we are reminded of the intricate connections between life, air, and the fragile balance necessary to sustain both. One of the fundamental challenges in terraforming a planet like Mars lies in creating a sustainable atmosphere that can support human life and terrestrial ecosystems. Unlike Earth, Mars has a thin atmosphere composed mostly of carbon dioxide, with only trace amounts of oxygen and nitrogen. To alter this environment, scientists have proposed several innovative methods that could gradually thicken the atmosphere and modify its composition. One approach involves the release of greenhouse gases, such as perfluorocarbons or methane, which have the capacity to trap heat and raise the planet's surface temperature. This warming effect could, over time, cause the sublimation of polar ice caps, releasing carbon dioxide and water vapor to further enhance atmospheric density and create a more hospitable climate. By carefully managing the introduction of these gases, it may be possible to initiate a feedback loop that incrementally transforms the Martian atmosphere into one more suitable for life. Another promising strategy centers on the idea of importing volatiles. Substances such as water, nitrogen, and noble gases, either from other celestial bodies or from within Mars itself. Some proposals suggest redirecting icy comets or asteroids rich in these elements to collide gently with the planet, delivering essential compounds needed to build a thicker, more Earth-like atmosphere. Alternatively, robotic mining operations might extract nitrogen trapped in Martian soil or release water from underground reservoirs. Introducing nitrogen is particularly important as it acts as a buffer gas that stabilizes atmospheric pressure and reduces the risk of harmful radiation reaching the surface. These methods require precise calculations and long-term planning, as the scale of material transfer would be immense, and the effects on planetary dynamics must be carefully monitored. Such endeavors exemplify the blend of creativity and caution necessary in planetary engineering. The process of reshaping a planet's atmosphere is inherently complex, demanding a delicate balance between technological intervention and natural planetary responses. For instance, while releasing greenhouse gases can warm a planet, excessive warming or unexpected chemical reactions could disrupt the delicate equilibrium needed for habitability. Additionally, the thin Martian gravity and weak magnetic field pose challenges by allowing lighter gases to escape into space more readily, necessitating continuous replenishment or innovative containment strategies. Understanding these factors compels scientists to develop adaptive terraforming plans that incorporate real-time environmental data and predictive modeling. The interplay of atmospheric chemistry, solar radiation, and planetary geology forms a dynamic system that must be respected and carefully guided. This scientific humility underscores the importance of patience and incremental progress as humanity explores the prospects of creating a new home beyond Earth. Beyond the physical and chemical alterations, creating a sustainable atmosphere also involves fostering biological components that can contribute to atmospheric stability. Introducing extremophile microbes or genetically engineered plants capable of surviving in harsh conditions may gradually produce oxygen and organic matter, enriching the atmosphere and soil. These living systems could work in concert with abiotic processes, enhancing the planet's capacity to retain heat and support more complex life forms over time. Such bioengineering approaches open new horizons in terraforming, blending biology with planetary science to craft ecosystems tailored to the unique conditions of another world. The integration of life itself as a tool for atmospheric transformation invites profound questions about the ethics and responsibilities inherent in planetary modification. As we consider these innovative methods for altering planetary atmospheres, it becomes clear that terraforming is not merely a technical challenge, but a multidisciplinary endeavor. It calls upon atmospheric physics, geology, biology, and engineering, as well as a deep appreciation for the intricate feedback loops that shape planetary environments. Each proposed intervention must be tested against a backdrop of uncertainty and long timelines, reminding us that patience and respect for natural processes are essential. The vision of creating a sustainable atmosphere on another world inspires us to expand our scientific horizons, while remaining mindful of the delicate balance we seek to establish. One of the most promising approaches to warming Mars involves the deliberate melting of its polar ice caps, which are composed primarily of carbon dioxide ice, along with some water ice. These frozen reservoirs represent a vast potential source of greenhouse gases, which, if released into the atmosphere, could help increase the planet's surface temperature. By introducing energy to these polar regions, perhaps through orbital mirrors focusing sunlight or other advanced heating technologies, the solid carbon dioxide would sublimate, transitioning directly from ice to gas. This process would thicken the thin Martian atmosphere, increasing atmospheric pressure and enhancing the greenhouse effect naturally. The thickened atmosphere would, in turn, retain more heat, gradually raising surface temperatures and creating conditions more favorable for liquid water. This approach is appealing because it leverages materials already present on Mars, reducing the need to import gases from elsewhere. Implementing such a strategy requires careful consideration of the complex interactions within the Martian climate system. The sublimation of the polar ice caps must be managed to avoid unintended consequences, such as destabilizing the polar regions or triggering dust storms that could temporarily reduce sunlight penetration. Additionally, the spatial distribution of warming is a key factor. Warming one pole more rapidly than the other could create atmospheric imbalances. Scientific models help predict how the atmosphere will respond, guiding the pacing and scale of interventions. It is also important to consider the long-term sustainability of the thickened atmosphere, as Mars's low gravity allows gases to escape into space over time. Therefore, continuous or periodic replenishment might be necessary, combining the melting of polar ice caps with other methods of greenhouse gas introduction. This layered approach underscores the importance of a delicate balance between technological capability and planetary stewardship. freezing temperatures, melting the polar ice caps could have cascading effects on Mars's potential habitability. Warmer temperatures and increased atmospheric pressure could allow liquid water to persist on the surface, a critical factor for life as we understand it. The release of water vapor from melting ice may further amplify the greenhouse effect, creating a positive feedback loop that accelerates warming. These changes could also support the gradual introduction of photosynthetic organisms, which might further modify the atmosphere by producing oxygen over extended periods. However, such transformations must be approached with caution, respecting the planet's existing environment and any potential native microbial life. The ethical implications of terraforming invite us to proceed thoughtfully, ensuring that our scientific curiosity does not overshadow the responsibility we hold toward other worlds. As we examine the practical steps necessary to initiate polar ice cap melting, engineering solutions emerge that are both imaginative and grounded in current scientific principles. Large space-based mirrors positioned in orbit could redirect and concentrate sunlight onto targeted polar regions, increasing the energy input without the need for massive on-site infrastructure. Alternatively, the deployment of dark, heat-absorbing materials on the ice caps could lower their albedo, causing them to absorb more solar radiation naturally. Each method presents unique challenges, including deployment logistics, energy requirements, and potential impacts on Mars's environment. These techniques demonstrate the intersection of planetary science and advanced engineering, highlighting the innovative spirit required to transform theoretical concepts into feasible terraforming actions. Ultimately, the endeavor to melt Mars's polar ice caps exemplifies the intricate dance between observation, modeling, and experimentation that defines terraforming efforts. It is a stepwise process, dependent on gradual atmospheric modifications that build upon one another. As the atmosphere thickens and temperatures rise, new opportunities for further interventions, such as the introduction of engineered microbes or the generation of additional greenhouse gases, will become viable. This gradual and measured approach respects the natural rhythms of planetary change, allowing us to learn and adapt our methods over time. From this vantage point, we can begin to imagine how the controlled transformation of Mars's climate might unlock new possibilities for human exploration and habitation in the distant future. Beyond the incremental warming of Mars through atmospheric adjustments, visionaries have considered more direct methods to increase the planet's energy intake. One such concept involves the deployment of colossal mirrors in orbit around Mars, designed to reflect and concentrate sunlight onto targeted regions of the surface. These orbital mirrors, floating silently in space, could amplify the natural light reaching Mars by redirecting solar radiation, much as a magnifying glass focuses rays to ignite a flame. By carefully positioning these reflective surfaces, it would be possible to warm specific areas, encouraging the sublimation of carbon dioxide ice or accelerating the melting of water ice reserves. This approach presents an elegant solution to the challenge of Mars's relative dimness, given its greater distance from the Sun compared to Earth. Constructing and deploying such vast mirrors is a task that pushes the boundaries of current engineering and material science. These structures would need to be both lightweight and durable, capable of withstanding the harsh environment of space while maintaining precise orientation. Advances in thin film materials and inflatable structures offer promising avenues, enabling the creation of mirrors spanning kilometers, yet weighing just a fraction of traditional spacecraft. Once in position, they could be controlled remotely or autonomously, adjusting angles to optimize sunlight reflection throughout Mars's day and seasonal cycles. The concept also introduces the possibility of modular designs, when numerous smaller mirrors work in concert to achieve a desired heating effect. This distributed system would provide resilience against damage and allow incremental scaling as technological capabilities evolve. Beyond Mars, the idea of orbital mirrors holds intriguing potential for terraforming other planets or moons with insufficient solar energy. For example, icy worlds on the fringes of our solar system could benefit from increased insolation, potentially transforming frozen surfaces into more hospitable environments. The mirrors could also serve dual purposes, acting as solar power collectors or communication relays, integrating terraforming efforts with broader infrastructure development. This multifaceted utility highlights the interconnected nature of space engineering projects, where a single technology can contribute to multiple goals simultaneously. Though still theoretical, the concept of orbital mirrors invites us to imagine a future where humanity harnesses the subtle interplay of light and shadow to shape new worlds. Implementing orbital mirrors would not only require technological innovation, but also deep consideration of planetary ecology and ethical stewardship. The deliberate alteration of a planet's climate through focused sunlight must be approached with caution, mindful of potential unintended consequences. Careful modeling and incremental testing would be essential to ensure that the intensified illumination does not trigger runaway effects or destabilize emerging ecosystems. These mirrors, while intangible and distant, represent a tangible step toward the active management of extraterrestrial environments. Their silent reflection of the sun's rays encapsulates the delicate balance between human ingenuity and the vastness of space. A balance that will guide our exploration of the cosmos for generations to come. While Mars often captures our imagination as the prime candidate for terraforming, Venus presents a dramatically different set of challenges that expand our understanding of planetary transformation. Unlike the cold and arid Martian surface, Venus is a world of intense heat and crushing pressure, wrapped in a thick atmosphere dominated by carbon dioxide and clouds of sulfuric acid. The planet's surface temperature soars to nearly 465 degrees Celsius, hot enough to melt lead, making it one of the most inhospitable places in the solar system. This stark contrast highlights that terraforming is not a one-size-fits-all endeavor. Each planet demands unique approaches tailored to its extreme conditions. The notion of reshaping Venus requires not only innovative technology, but also a profound reimagining of how we might engineer entire planetary climates and atmospheres from scratch. The monumental effort to terraform Venus would begin with addressing its runaway greenhouse effect, a phenomenon that traps solar energy and heats the planet to searing levels. This situation arose due to a thick carbon dioxide-rich atmosphere, which sustains a pressure over 90 times that of Earth's surface. To counteract these conditions, scientists have proposed a variety of theoretical interventions, such as deploying massive solar shades or mirrors in space to reduce solar heating. Another concept involves chemically removing carbon dioxide from the atmosphere through advanced industrial processes, or introducing genetically engineered organisms capable of transforming atmospheric gases. Each method carries immense technical and logistical barriers, yet collectively they broaden the scope of what terraforming might entail, pushing the boundaries of planetary engineering beyond mere temperature adjustments to fundamental atmospheric restructuring. Beyond the physical and chemical hurdles, terraforming Venus also challenges us to rethink the timescales and ethical considerations of planetary modification. Unlike Mars, where changes might be observable within decades, Venus's thick atmosphere and intense conditions imply that any terraforming efforts would span centuries or even millennia. The scale of intervention required demands patience and a long-term vision that transcends immediate human lifespans. Furthermore, altering Venus's environment raises questions about our responsibility toward untouched worlds, the potential for unknown ecological outcomes, and the value of preserving planetary diversity. These considerations remind us that terraforming is not merely a scientific or engineering challenge, but a philosophical one as well, calling for humility and foresight as we contemplate reshaping entire worlds. Exploring the complexities of Venus alongside Mars enriches our understanding of terraforming as a multifaceted pursuit, revealing a tapestry of planetary environments, each with its own set of mysteries and demands. Where Mars invites visions of ice melting and atmosphere thickening, Venus confronts us with extremes of heat and pressure, prompting innovative approaches that may one day redefine what it means to make a planet habitable. This broadened narrative encourages us to consider how future technologies and scientific insights might unlock new possibilities, allowing humanity to adapt not only to a single world, but to the diverse and dynamic environments scattered across our solar system. Such reflections naturally lead us toward examining the delicate interplay of planetary systems, setting the stage for the next steps in our cosmic journey. Venus presents an extraordinary challenge for those who imagine transforming its environment into one that could support life as we know it. The planet's atmosphere, composed predominantly of carbon dioxide, traps heat with astonishing efficiency, creating surface temperatures that exceed 400 degrees Celsius. This intense greenhouse effect, combined with crushing atmospheric pressure, nearly 100 times that of Earth, makes Venus an inhospitable world in its current state. Yet it is precisely these extreme conditions that inspire innovative cooling strategies aimed at gradually reducing surface temperatures and pressure to more manageable levels. One such approach involves the deployment of solar shades, massive, thin structures positioned between Venus and the Sun. These shades would act as a giant parasol, reflecting or absorbing a portion of solar radiation before it reaches the planet, thereby lowering the heat input and allowing the atmosphere to cool naturally over time. Another compelling method to cool Venus's atmosphere is atmospheric scrubbing, a process that would remove carbon dioxide and other greenhouse gases from the dense air. This could be achieved through advanced chemical or biological means, where engineered microbes or catalysts convert carbon dioxide into solid carbonates or other stable compounds that could be sequestered on the planet's surface or below it. Such scrubbing technologies require breakthroughs in materials science and synthetic biology, but they hold the promise of gradually thinning the atmosphere and decreasing the surface pressure. As the atmosphere becomes less dense and less heat is trapped, surface temperatures would drop, potentially allowing the introduction of water and the gradual development of a more Earth-like climate. These processes would unfold over centuries or even millennia, reflecting the immense scale and complexity of planetary engineering. Beyond direct atmospheric intervention, the concept of altering Venus's albedo, the measure of how much sunlight the planet reflects, offers further possibilities to cool the planet. Increasing the reflectivity of Venus's thick cloud layers, perhaps by injecting reflective aerosols or modifying cloud chemistry, could reduce the amount of solar energy absorbed at the surface. Such geoengineering techniques would require precise control to avoid unintended consequences, but they demonstrate how subtle manipulations of planetary systems could produce significant changes in climate. The interplay between solar shades, atmospheric scrubbing, and albedo modification illustrates a multifaceted approach where multiple technologies work in concert to reshape the environment. These strategies underscore the potential of future engineering to transform even the most forbidding planets into worlds capable of sustaining life. Cooling Venus's atmosphere and making it habitable is not merely a technical challenge, but also a profound exercise in planetary stewardship. It demands a deep understanding of atmospheric physics, chemistry, and the delicate balances that govern climate systems. The task invites us to expand our imagination and ingenuity, envisioning a future where humanity's reach extends beyond Earth's cradle. Each step toward tempering Venus's fiery embrace embodies a commitment to long-term thinking and respect for planetary complexity. As we explore these possibilities, we are reminded that terraforming is not a singular act, but a continuous dialogue between science and nature, technology and ethics. This evolving conversation prepares us for the next stages of exploration, where the lessons learned here will inform our efforts on other worlds and in broader cosmic contexts. When we turn our gaze from Venus to the Moon, the idea of terraforming takes on a distinctly different character. Unlike the dense, toxic atmosphere of Venus that requires cooling and cleansing, the Moon presents a landscape almost entirely devoid of air and water, bathed in harsh solar radiation and marked by extreme temperature fluctuations. Its lack of a substantial atmosphere and magnetic field means it is constantly exposed to cosmic rays and solar winds, conditions that pose significant obstacles to creating a stable environment suitable for human habitation. Yet, within these stark limitations lies an intriguing opportunity to reimagine what terraforming might mean beyond the familiar boundaries of Earth-like worlds. The Moon's surface, composed largely of regolith and volcanic basalt, offers raw materials that could be harnessed in the process of building habitats and sustaining life. Potential methods of terraforming might involve generating a thin atmosphere through the release of trapped gases or importing volatiles from other celestial bodies, gradually building a protective layer to shield future inhabitants from harmful radiation. Advances in technology may allow us to create enclosed biospheres or magnetic shields that mimic Earth's protective qualities, offering a semblance of a terrestrial environment. These efforts, however, would require immense energy and resources, raising questions about feasibility and the long-term sustainability of such endeavors. Another intriguing aspect of lunar terraforming is the possibility of using the Moon as a stepping stone for broader space exploration. Its low gravity and proximity to Earth make it an ideal candidate for developing infrastructure that supports human expansion into the solar system. Terraforming efforts here might not seek to replicate Earth's atmosphere entirely, but instead focus on creating livable zones tailored to human needs, leveraging technology to compensate for the Moon's natural deficiencies. This shift in perspective challenges us to reconsider terraforming not as the creation of perfect Earth analogs, but as the adaptation of environments in ways that are practical and harmonious with local conditions. In contemplating the Moon's potential as a terraforming target, we uncover a spectrum of challenges that extend beyond mere engineering. Ethical considerations arise, inviting reflection on our responsibilities when altering another world's pristine environment. The Moon, a silent witness to Earth's history and a symbol of human aspiration, reminds us that terraforming is as much about respect and stewardship as it is about innovation. Each step forward in this cosmic journey encourages careful deliberation, ensuring that our actions honor both scientific exploration and the preservation of celestial heritage. As we continue to explore these themes, we open pathways to understanding how terraforming might evolve across diverse environments within our solar system. At the heart of terraforming lies the subtle interplay between biology and planetary science, where microorganisms emerge as quiet yet powerful agents of transformation. These microscopic lifeforms, resilient and adaptable, offer a unique toolkit for altering extraterrestrial environments. Through bioengineering, scientists envision harnessing microbes to initiate foundational changes, such as generating breathable oxygen or enriching barren soils to gradually make alien worlds more hospitable to human life. In this vision, microorganisms function as living catalysts, capable of surviving harsh conditions and performing essential biochemical processes that machines alone cannot replicate. Their natural abilities to fix nitrogen, break down minerals, and produce organic compounds suggest a profound synergy between the biological and geological realms, opening new pathways for sustainable planetary modification. One of the foremost challenges in terraforming is creating an atmosphere that can support terrestrial life. And here, photosynthetic microbes present a promising solution. Cyanobacteria, for example, are ancient organisms known for their ability to convert carbon dioxide into oxygen through photosynthesis. Introducing such microorganisms to a planet with a thin or inhospitable atmosphere could, over extended periods, incrementally increase oxygen levels, gradually crafting an environment more favorable to complex organisms. This process, reminiscent of Earth's own great oxygenation event billions of years ago, illustrates how life itself can drive planetary change. By carefully selecting and engineering microbial strains to withstand extreme temperatures, radiation, and chemical compositions, researchers aim to tailor these organisms to thrive beyond Earth. Beyond atmospheric modification, microorganisms hold potential for transforming the very ground beneath our feet, or rather, beneath our future habitats. Soil on many planets and moons is often devoid of the organic components necessary to support plant life, lacking nutrients and biological activity. Microbes can play a vital role in this context by breaking down mineral substrates, recycling nutrients, and fostering the formation of fertile soil. Through processes such as bioleaching and nitrogen fixation, engineered microbial communities could convert sterile regolith into a nurturing medium for vegetation. This biological groundwork is essential for establishing self-sustaining ecosystems that include plants, animals, and ultimately human settlers. Such integration underscores the importance of understanding microbial ecology and genetics, as well as the delicate balance required to introduce life without unintended consequences. The convergence of bioengineering and planetary science invites us to consider the ethical dimensions intertwined with microbial terraforming. While microbes offer incredible promise for altering environments, their introduction must be approached with caution to avoid disrupting any native, possibly undiscovered life forms. The prospect of seeding another world with terrestrial microbes raises profound questions about contamination, planetary protection, and our role as cosmic stewards. Responsible research entails rigorous study of microbial survivability, containment strategies, and long-term ecological impacts. These considerations reflect a growing recognition that terraforming is not merely a technical challenge, but also an ethical journey, one that demands humility and foresight as we extend life beyond Earth's cradle. As we explore the potential for microorganisms to serve as pioneers in terraforming, we begin to glimpse a future where biology and technology merge harmoniously to shape new worlds. The delicate task of engineering life to foster habitability requires patience, precision, and profound respect for both known and unknown ecosystems. This harmonious blending of disciplines paves the way toward more ambitious endeavors, where bioengineered organisms could be tailored not only to survive, but to thrive and support complex biospheres. Our understanding of microbial roles thus becomes a gateway to imagining how terraforming might unfold across the diverse environments of our solar system and beyond. When we consider the grand challenge of terraforming planets, it becomes immediately clear that we are engaging with processes that unfold across vast stretches of time. Unlike many human endeavors that yield results within months or years, terraforming demands a perspective that embraces centuries, even millennia. This is not a project for instant gratification. Instead, it invites us to adopt a patient and measured outlook, one that acknowledges the slow rhythms of planetary change. From altering atmospheric composition to stabilizing surface conditions, each phase requires careful monitoring and gradual adjustment. In this way, terraforming is a practice of stewardship on a cosmic scale, where progress is best measured not in days or decades, but in generations. Patience is more than a virtue in terraforming. It is a necessity grounded in the laws of physics, chemistry, and biology. The transformation of an entire planet involves chemical reactions that may take centuries to shift atmospheric gases to hospitable levels, or geological processes that slowly release or sequester key compounds. Biological interventions, such as introducing microorganisms or engineered plant life, rely on ecosystems gradually establishing balance and resilience. Each step unfolds incrementally, shaped by feedback loops and environmental variables that cannot be rushed without risking unintended consequences. This measured pace allows for observation, learning, and adaptation, ensuring that terraforming efforts remain aligned with the evolving conditions of the target world. Such timescales challenge our conventional sense of urgency, but enrich our appreciation for the delicate interplay of natural forces. Embracing long-term timescales also deepens our philosophical understanding of humanity's place in the universe. Terraforming is not merely a technological feat, it is a commitment to nurturing life beyond Earth with humility and foresight. As we contemplate projects that span centuries, we recognize the importance of intergenerational collaboration and the transmission of knowledge across vast stretches of time. The slow march toward habitability invites us to think beyond immediate needs and desires, fostering a connection to future inhabitants of these transformed worlds. This cosmic patience encourages a mindset of sustainability and respect, reminding us that the seed we plant today may only flourish long after we are gone. In this way, terraforming becomes a profound expression of hope and stewardship. Moreover, Understanding the immense timescales involved helps set realistic expectations for what terraforming can achieve and when. It tempers the enthusiasm for rapid planetary makeover with a sober recognition of the natural constraints we face. The patience required is not passive waiting, but an active engagement with planetary systems guided by science and observation. Each incremental change builds a foundation for the next, creating a layered process of environmental evolution. This perspective encourages us to celebrate small milestones and subtle shifts, knowing they are essential steps toward eventual habitability. The vastness of time involved invites awe and respect, inspiring us to think deeply about the legacy we wish to create beyond our home planet. As we continue to explore the complexities and possibilities of terraforming, this awareness of long-term commitment naturally leads us to consider the practical and ethical dimensions of such endeavors. The patience required not only challenges our technological capabilities, but also our societal values and priorities. It prompts questions about stewardship, responsibility, and the kind of future we envision for humanity among the stars. This evolving dialogue frames the next steps in terraforming research and implementation, inviting a thoughtful integration of science, ethics, and imagination as we look ahead to shaping new worlds. As humanity contemplates the monumental task of terraforming distant planets, it becomes increasingly clear that the scientific and technical challenges are only one aspect of a much broader conversation. At its heart, terraforming raises profound ethical questions about our right to alter environments beyond Earth. These questions invite us to reflect deeply on the consequences of imposing human-centric ecosystems on alien worlds, which may be untouched and pristine in their own natural states. The act of transforming an entire planet is not simply an exercise in engineering. It is, in essence, a form of planetary stewardship that demands humility, foresight, and profound respect for the unknown. How do we balance our desire to expand and survive with the obligation to preserve and honor other worlds? These considerations extend beyond practical concerns to touch on the very nature of humanity's relationship with the cosmos. Another layer of ethical reflection emerges when we consider the possibility of indigenous life forms, no matter how microbial or simple, that might exist on these planets. The discovery of extraterrestrial life, even in its most basic forms, would compel us to rethink our approach to terraforming with heightened caution and sensitivity. The moral imperative to avoid harm to alien ecosystems echoes the principles that guide conservation efforts on Earth, yet it is amplified by the scale and irreversibility of planetary alteration. In this context, terraforming becomes not only a scientific venture, but a moral dialogue about coexistence, respect, and the prevention of inadvertent destruction. It challenges us to develop robust frameworks that guide decision-making processes, ensuring that expansion into space does not become a form of ecological imperialism, but rather an ethical extension of our stewardship responsibilities. The question of time also enriches the ethical dimension of terraforming. These processes unfold over centuries or even millennia, far beyond the lifespan of any individual or generation. This temporal scale invites us to think about intergenerational justice and the rights of future inhabitants, both human and otherwise. When we initiate terraforming, we are effectively making decisions on behalf of countless beings yet to come, shaping the conditions of life long after our own presence has faded. This responsibility demands a vision that transcends immediate gains or conveniences, asking us to cultivate patience, wisdom, and a deep sense of accountability. It also challenges our political and social systems to incorporate long-term thinking, ensuring that the futures we design are equitable, sustainable, and mindful of the diverse stakeholders involved. Finally, the ethical considerations surrounding terraforming invite us to explore the philosophical dimensions of identity and belonging in the cosmos. As humans reach beyond Earth, the act of reshaping alien environments raises questions about what it means to be a part of the universe. Should humanity seek to imprint its own image on other worlds, or is there value in preserving the natural state of these places as expressions of cosmic diversity? This dialogue encourages a humble approach, one that recognizes our species as a part of a vast and complex system rather than its master. It provokes a thoughtful reflection on our responsibilities, not only as explorers and innovators, but as caretakers of planetary legacies. In embracing this contemplative stance, we open pathways to more thoughtful, respectful, and harmonious interactions with the unknown, guiding the journey of terraforming toward wisdom as much as progress. In the quiet pursuit of understanding how we might one day transform distant worlds, scientists and engineers have embarked on a series of deliberate experiments designed to unravel the complexities of planetary environments. Among the most compelling endeavors are Mars simulation habitats, carefully constructed to mimic the atmospheric, geological, and biological conditions of the red planet. These habitats, often situated in remote deserts or volcanic regions on Earth, serve as test beds for human adaptation and technological resilience. Researchers live and work within these isolated modules for extended periods, refining life support systems, testing agricultural techniques, and studying psychological effects of confinement in a controlled environment. Such experiments do more than prepare astronauts for future missions. They provide invaluable data about sustaining life beyond Earth, revealing both the fragility and potential of human existence in alien settings. Parallel to habitat simulations, atmospheric experiments continue to probe the possibility of altering planetary climates to support life. On Mars, for example, scientists have theorized methods to thicken the thin carbon dioxide atmosphere, increasing surface pressure and temperature to create more hospitable conditions. Laboratory studies and computer models explore the effects of introducing greenhouse gases, such as perfluorocarbons, that could amplify warming through radiative forcing. Meanwhile, field experiments on Earth examine the behavior of microbes and extremophiles, organisms thriving in some of our planet's harshest environments, as analogues for potential biological agents capable of contributing to atmospheric modification. These investigations bridge microbiology, chemistry, and planetary science, illustrating the intricate interplay required to initiate even modest planetary change. The slow, methodical nature of this work underscores the patience and precision necessary in contemplating terraforming as a realistic endeavor. Beyond Mars, research extends to other celestial bodies where the challenges of terraforming vary in scale and complexity. For instance, the icy moons of the outer solar system, such as Europa and Enceladus, inspire studies on subsurface ocean habitability and the potential for introducing or nurturing life in concealed aquatic environments. Robotic missions equipped with advanced instruments gather data on surface composition, radiation levels, and thermal activity, informing hypotheses about how to create stable, life-supporting niches beneath ice crusts. In parallel, terrestrial analog sites, glaciers, deep sea vents, and polar deserts offer natural laboratories to test instruments and study extremophile organisms that might survive in these alien habitats. This multifaceted approach highlights the necessity of interdisciplinary collaboration, combining planetary science, astrobiology, and engineering to gradually translate terraforming from speculative vision into achievable science. Alongside physical and biological experiments, technological innovation plays a crucial role in advancing terraforming research. Development of autonomous systems, for instance, aims to deploy robotic agents capable of conducting preliminary environmental modifications and maintenance without direct human intervention. These machines might release gases, cultivate microorganisms, or manage energy inputs to instigate slow but steady planetary transformation. Simultaneously, advancements in materials science contribute to designing habitats and infrastructures resilient to extreme conditions, ensuring human presence can be sustained safely. The integration of artificial intelligence further enhances the capacity to monitor and adapt terraforming processes in real time, enabling responsive adjustments to unforeseen variables. Together, these technological strides form the backbone of pragmatic efforts, grounding terraforming in achievable milestones rather than distant dreams. Through these ongoing studies and experimental frameworks, the vision of terraforming is steadily anchored in the realm of real-world science. Each habitat trial, atmospheric model, and robotic mission adds a piece to the intricate puzzle of reshaping alien worlds thoughtfully and responsibly. The measured pace of progress reflects a deep respect for the complexity of planetary systems and an awareness of the profound consequences that accompany such transformations. As we continue to explore and experiment, we cultivate not only technical knowledge, but also a broader understanding of our place in the cosmos, preparing gently and deliberately for the possibility of becoming stewards of new worlds. This foundation of empirical research invites us next to consider the broader implications and future directions of terraforming endeavors. The journey toward terraforming distant planets unfolds as a grand challenge that demands remarkable technological innovations. At the heart of this endeavor lies the advancement of robotics, which must evolve far beyond today's capabilities. Autonomous machines will be essential for conducting delicate operations in harsh and remote environments, from constructing habitats to manipulating planetary surfaces. These robots will need to operate with precision, resilience, and adaptability, often untethered from direct human control for extended periods. Their ability to sense, analyze, and respond to dynamic conditions will make them indispensable pioneers on alien worlds, preparing the groundwork for future human presence. By pushing the boundaries of robotic technology, we set the stage for a new era of exploration and transformation, where synthetic agents become our hands and eyes in places yet untouched. Complementing robotics, the development of advanced energy systems stands as a cornerstone of terraforming technology, delivering reliable, sustainable power in environments light years away from Earth requires novel approaches to capture, store, and distribute energy efficiently. Solar energy, while abundant, may be limited by planetary distance and atmospheric conditions, prompting exploration into nuclear fusion or next-generation reactors that can operate safely and continuously in space. Energy storage and transmission technologies must also evolve, ensuring that power is available whenever and wherever needed to support life support systems, atmospheric modification processes, and robotic operations. These breakthroughs in energy science will not only fuel the transformation of planetary environments, but also inspire innovations that ripple through terrestrial applications, igniting a future where humanity thrives both on and beyond its home planet. Equally essential to these advancements is the progress in materials science, which underpins the construction of habitats, protective gear, and infrastructure needed to sustain life on altered worlds. Materials must be engineered to withstand extreme temperatures, radiation, and corrosive atmospheres, often for prolonged durations. Innovations in lightweight composites, self-healing surfaces, and adaptive shielding technologies will provide the resilience necessary for long-term habitation. Furthermore, the ability to utilize in situ resources, mining and processing local minerals and elements, will reduce reliance on Earth-based supplies, making terraforming efforts more sustainable and feasible. This synergy between materials science and planetary resource utilization opens new vistas for creating environments that support biological processes, effectively bridging the gap between inhospitable terrain and human comfort. The interplay between these technological fields, robotics, energy, and materials science, illustrates the multidisciplinary nature of terraforming. Each advancement not only addresses specific challenges, but also harmonizes with others to create a comprehensive toolkit for planetary transformation. The collaborative efforts of researchers, engineers, and visionaries working across these domains drive the steady progress that turns speculative ideas into tangible possibilities. As we anticipate these future breakthroughs, we also recognize the importance of integrating ethical frameworks and environmental stewardship into technological development, ensuring that the marvels we create honor the delicate balance of ecosystems we aim to establish. This holistic approach to innovation invites us to imagine a future where technology empowers humanity to become gentle cultivators of new worlds. As these technologies evolve, they will unlock pathways not only for terraforming, but also for expanding our presence throughout the solar system and beyond. The essential advancements in robotic autonomy, energy generation, and material resilience form the foundation upon which future missions will build, gradually transforming visions into realities. With each incremental achievement, the prospect of reshaping planetary environments moves closer to fruition, inviting us to embrace the responsibilities and opportunities that accompany such power. This unfolding narrative of innovation and exploration naturally leads us to consider the broader implications and strategic planning necessary for sustained human settlement in these newly forged worlds. The promise of terraforming extends beyond mere scientific curiosity. It holds the potential to redefine the future of humanity itself. By transforming barren, inhospitable planets into vibrant, life-supporting environments, we open the door to new homes for generations to come. As Earth's resources face increasing pressures from population growth and environmental challenges, these newly habitable worlds could provide much-needed relief, offering space for human communities to flourish. The ability to expand our living horizons would not only safeguard our species against existential risks, but also inspire a renewed sense of purpose and unity, rooted in the shared endeavor of cosmic stewardship. The vastness of space stands no longer as a barrier, but as an invitation to nurture life in places once thought unreachable. Beyond the immediate benefits of habitation, terraforming offers profound opportunities for scientific discovery. Each planet presents a unique environment with its own geological and atmospheric intricacies, waiting to be understood and harmonized with human needs. The process of altering a planet's climate and ecosystem will inevitably deepen our knowledge of planetary sciences, atmospheric chemistry, and biology. Learning how to cultivate ecosystems under radically different conditions may reveal new insights into the origins of life and the delicate balances that sustain it. Moreover, the technologies developed for terraforming could translate into innovative solutions for environmental challenges here on Earth, creating a symbiotic relationship between planetary engineering and terrestrial conservation. Such endeavors encourage a holistic approach to science, where exploration and preservation inform one another. Resource acquisition is another compelling advantage offered by terraforming. Planets and moons within our solar system contain abundant materials, including minerals, water ice, and rare elements critical for advanced technologies. By establishing self-sustaining colonies on these worlds, humanity can access these resources more directly, reducing the strain on Earth's ecosystems and supply chains. This expansion could lead to the development of off-world industries powered by renewable energy sources and guided by environmental responsibility. The integration of these extraterrestrial resources into human economies supports not only growth, but also innovation, as new materials and conditions inspire novel applications and technologies. In this way, terraforming acts as a catalyst for sustainable development on a cosmic scale. The horizon of possibility broadens, inviting us to imagine a future where human ingenuity harmonizes with the cosmos. The journey toward terraforming also invites reflection on the ethical and philosophical dimensions of our role in the universe. As we gain the power to reshape entire worlds, we must consider the responsibilities that come with such influence. The deliberate creation of habitable environments demands careful stewardship, respect for potential indigenous ecosystems, and the commitment to equitable access. These considerations foster a deeper connection between humanity and the cosmos, where exploration is balanced by humility and foresight. Embracing this mindset encourages collaboration across nations and disciplines, uniting us in a shared vision of hope and resilience. In the quiet expanse of space, our aspirations become intertwined with the delicate art of planetary transformation. Throughout the decades, terraforming has captured the imagination of storytellers and audiences alike, emerging as a profound theme in science fiction literature and cinema. These creative works often explore the transformative power of humanity to shape distant worlds, crafting narratives that blend scientific possibility with deep philosophical inquiry. From classic novels to contemporary films, the portrayal of terraforming serves not only as a speculative exercise, but also as a mirror, reflecting our hopes, fears, and ethical dilemmas about our expanding presence in the cosmos. These stories invite us to consider what it means to create life-sustaining environments beyond Earth, drawing us into a shared dream of interplanetary habitation. Such imaginative depictions provide fertile ground for exploring the technical challenges and moral questions inherent in altering alien landscapes, allowing audiences to engage with complex ideas in accessible and emotionally resonant ways. In many iconic films, terraforming is portrayed as a grand endeavor, often characterized by sweeping visuals of barren planets gradually blossoming into vibrant ecosystems. These cinematic interpretations frequently highlight both the awe-inspiring potential and the unforeseen consequences of planetary engineering. For example, stories may emphasize the delicate balance between technological mastery and ecological sensitivity, reminding viewers that the act of terraforming is not merely a scientific feat, but also an ethical commitment. By dramatizing the challenges of sustaining life on foreign worlds, these narratives encourage reflection on our relationship with nature and the responsibilities we bear as potential cosmic gardeners. Through such visual storytelling, the concept of terraforming transcends abstract theory and becomes a tangible aspiration, inspiring curiosity and a sense of wonder about humanity's future among the stars. Literature, too, has long embraced terraforming as a rich thematic element, weaving it into stories that explore human identity, adaptation, and coexistence with alien environments. Writers often use the process of planetary transformation as a metaphor for renewal and change, probing the resilience of life and the adaptability of cultures in new and challenging settings. These narratives frequently raise important questions about colonization, environmental stewardship, and the ethical use of technology. By envisioning worlds that evolve under human influence, authors invite readers to grapple with the responsibilities tied to such power, fostering a nuanced understanding of how our actions ripple across time and space. In this way, the literary dimension of terraforming enriches our collective imagination, offering both cautionary tales and hopeful visions that resonate deeply with readers across generations. The resonance of terraforming in popular culture also serves an important role in bridging scientific discourse with public interest and engagement. By embedding scientific concepts within compelling stories, movies and books make complex ideas more approachable, sparking curiosity and encouraging dialogue about the future of space exploration. This cultural interplay cultivates a broader appreciation for the challenges and possibilities of planetary transformation, inspiring new generations to pursue knowledge and innovation. Moreover, it fosters a shared sense of wonder and responsibility as audiences come to see terraforming not just as a distant ambition, but as a collective journey that unites humanity's curiosity and creativity. Through this dynamic exchange between science and storytelling, terraforming continues to fuel both imagination and inquiry, laying the groundwork for real-world advancements yet to come. As we reflect on the rich tapestry of ideas woven by popular culture around terraforming, it becomes clear that these stories do more than entertain. They shape our vision of what might be possible in the far reaches of space. They invite us to dream boldly while remaining mindful of the delicate balance required to nurture life beyond Earth. This interplay between imagination and reality encourages a thoughtful approach to planetary transformation, where creativity and caution coexist. In this ongoing narrative, we find a profound connection between human aspiration and the evolving science of terraforming, a connection that continues to inspire exploration and discovery. And so, with our minds open to both the wonders and challenges ahead, we turn now to the scientific principles that underpin these visions, delving deeper into the fascinating process of making new worlds habitable. As we stand at the threshold of what may be humanity's next great adventure, the concept of terraforming invites us to contemplate not only the transformation of distant worlds, but also the transformation within ourselves. The ambition to reshape barren landscapes into thriving ecosystems speaks to a deep-seated desire to expand the domain of life, to reach beyond the confines of our single blue planet. Yet this endeavor is not merely a scientific challenge. It is a profound ethical and philosophical journey. It asks us to consider how we might balance our technological capabilities with respect for the environments we seek to alter. Each step forward in terraforming research reminds us of the responsibility that accompanies such power, to act with foresight, humility, and care. The path ahead will demand patience, collaboration, and innovation, weaving together fields as diverse as planetary science, ecology, engineering, and ethics. It is a venture that mirrors the complexity of life itself, requiring us to embrace uncertainty while nurturing hope. Looking toward the horizon, the potential of terraforming extends beyond mere survival. It offers a vision of renewal and possibility. The idea that humanity might cultivate new worlds where life can flourish kindles a sense of wonder and purpose. It challenges us to rethink our place in the cosmos, to envision a future where our species is truly interplanetary. This vision is grounded in rigorous scientific exploration, understanding atmospheric chemistry, planetary geology, and the delicate interplay of biological systems. It is through this lens that terraforming becomes not just a dream, but a tangible goal, shaped by incremental advances and careful experimentation. As we refine our techniques and deepen our understanding, we lay the groundwork for future generations to inherit a universe enriched with diverse habitats and opportunities for life to thrive. Yet, even as we embrace the promise of terraforming, we must remain mindful of the profound unknowns that accompany such grand endeavors. The complexity of planetary ecosystems, the unpredictability of environmental feedbacks, and the ethical considerations of altering alien worlds all underscore the need for cautious progression. The journey of terraforming is not a sprint, but a measured exploration, inviting us to learn from each discovery and to adjust our course with wisdom and care. It is a testament to human resilience and creativity, reflecting our enduring quest to understand and harmonize with the cosmos. In this ongoing quest, every challenge encountered becomes a lesson, every obstacle an opportunity to deepen our connection to the universe and to one another. Ultimately, the story of terraforming is a story of hope, a hope that transcends the boundaries of Earth, reaching out toward the stars with a spirit of curiosity and stewardship. It calls upon us to imagine the unimaginable, to participate in a legacy that may one day transform barren worlds into vibrant homes. As we conclude this reflection, let us carry forward this vision with gentle determination, honoring the delicate balance between exploration and preservation. In doing so, we become part of a grand narrative that stretches across space and time, a narrative that invites each of us to dream, to discover, and to contribute to humanity's next giant leap. The universe awaits, vast and full of potential, and with open hearts and minds, we prepare to embrace the journey ahead.